So today we're going to solve October-November 2022, paper 42. Okay. Question number 1 says calcium chloride, CaCl2, is an ionic solid. The values of some energy changes are shown in table 1.1. So here are some energy changes that they've shown in this table. Part A says define lattice energy. So lattice energy is the enthalpy change. Okay, it's the enthalpy change or the energy change. So the enthalpy change or energy change when 1 mole of an ionic solid or an ionic lattice is formed from its constituent gaseous ions under standard conditions. Okay. Constituent gaseous ions under standard conditions. Use the data in table 1.1 to calculate the standard enthalpy change of formation of calcium chloride. It may be helpful to draw an energy cycle. Show all your working. Here we have to draw a Born-Haber cycle, right? That's an application of Hess's law. A Born-Haber cycle is used to calculate the lattice enthalpy, right? So the best thing to do here is to start with the elements, right? So we have calcium solid and chlorine gas, right? And we want to find the enthalpy change of formation. The enthalpy change of formation is the enthalpy change when these elements in their standard state form 1 mole of a compound. In this case, the compound that we have is calcium chloride. So we want 1 mole of calcium chloride forming, right? We want 1 mole of calcium chloride solid forming. So that's our unknown, right? And as far as the enthalpy change of formation is concerned, right, what we can do here is we can directly convert the elements to the ionic compound, or we can first convert the elements to the gaseous ions and then convert the gaseous ions to the solid lattice, right? So what we can do here is we can first convert calcium into its gaseous ion, right? So what we're going to do here is we're going to first atomize calcium. The enthalpy change of atomization is the enthalpy change or the energy needed to form 1 mole of gaseous ions. So here the atomization of calcium is 193, positive 193. So that's the enthalpy change when 1 mole of gaseous chlorine atoms are formed from the element, right? In this case the solid. So we have gaseous chlorine atoms plus Cl2, right? So that's enthalpy change of atomization of calcium. That's positive 193, positive 193. Then we're going to ionize calcium, right? We want to make calcium 2 plus, so that's going to be the first and the second ionization energy, right? So first plus second ionization energy of calcium. That's going to be plus 590 plus 1150, right? So we have plus 590 plus 1150. And now we have gaseous calcium ions, Ca2 plus gaseous, and we have Cl2 gas, right? And then what we can do is, now that we have the gaseous calcium ions, right, we want gaseous chlorine ions. So first we're going to convert the chlorine molecules into chlorine atoms, right? That's atomization of chlorine, but that's for 1 mole of gaseous atoms forming from the element in its standard state. We want 2 moles of chlorine atoms, right? We want 2 moles of chlorine atoms. So we're going to have 2 times the atomization of chlorine, right? So that will be 2 times positive 121, 2 times enthalpy change of atomization of chlorine. That will be 2 times positive 121. And what we get is, we have the gaseous calcium ions, and now we have 2 moles of gaseous chlorine atoms. And then we're going to form 2 moles of gaseous chloride ions. So that will be the electron affinity of chlorine. And again, it will be 2 times the electron affinity because we have 2 moles of chloride ions forming. Okay, so 2 times the electron affinity of chlorine, right? The first electron affinity is exothermic, so that's negative 364 here, right? So that is 2 times negative 364. Again, exothermic, we're going to use a downward arrow, right? And now we have our gaseous ions. So we have our gaseous ions here. So what we have here is we have Ca2 plus gaseous, and we have 2Cl minus gaseous, and then lastly the enthalpy change when the solid lattice is formed and 1 mole of the solid lattice is formed from the gaseous ions. That is your lattice enthalpy, which is negative 2237 kilojoules per mole. So this is minus 2237. Right, so we can say that we can directly convert the elements into the solid ionic lattice. That's the enthalpy change of formation, and that is equal to 193 plus 590 plus 1150 plus 2 times 121 plus 2 times negative 364 minus 2237. Again, directly convert the elements into the solid lattice, or first convert the elements to the gaseous ions and then convert the gaseous ions to the solid lattice. So we can say the enthalpy change of formation is equal to 193 plus 1150 plus 590 plus 2 times 121 plus 2 times negative 364 minus 2237. Okay, and the answer over here should come out to negative 790 kilojoules per mole. Okay, negative 790. So that's the answer. All right, let's move on to part C. 3 possible values for the first electron affinity of bromine are shown in table 1.2. One of them is correct. Place a tick by the correct value. Explain your choice. So from the table above, we know that the electron affinity of chlorine, the first electron affinity of chlorine is negative 364 kilojoules per mole, right? And bromine is below chlorine in the periodic table. Now, the electron affinity is a measure of the tendency of an atom to gain electrons. The more exothermic it is, the more favorable gaining electrons is. Now, we know that down the group, the tendency to gain electrons decreases, right? Because bromine has more shells, right? It's a larger atom, right? Which means that the incoming electron experiences a weaker nuclear attraction because of the greater distance and the greater shielding, right? And because there's a relatively weaker nuclear attraction, right, the process is less exothermic. Okay, the first electron affinity of bromine will be less exothermic because lesser energy will be released because a weaker attraction would form. So we can say that it will be less exothermic than the first electron affinity of chlorine. And the explanation here is that it's less exothermic because down the group, right, down the group, the number of shells increases, therefore shielding and atomic radius increases, right? Hence, the incoming electrons experience weaker nuclear attraction, okay? Weaker nuclear attraction. So the first electron affinity is less exothermic, okay? Less exothermic. The enthalpy change of hydration of the chloride ion can be calculated using the lattice energy of calcium chloride and the data shown in table 1.3. Define the following terms: enthalpy change of solution and enthalpy change of hydration. So what's the enthalpy change of solution? So the enthalpy change of solution is the enthalpy change, okay, the enthalpy change when 1 mole of a substance, okay, when 1 mole of a substance. In our syllabus, we study ionic solids most of the time, right? But it applies to any substance. So when 1 mole of a substance, or you can say solid, okay, dissolves in sufficient water to form an infinitely dilute solution. Okay, sufficient water to form an infinitely dilute solution. Enthalpy change of hydration, on the other hand, specifically refers to the enthalpy change when 1 mole, the enthalpy change when 1 mole of a gaseous ion, okay, and 1 mole of a gaseous ion dissolves in sufficient water to form an infinitely dilute solution, okay, dissolves in sufficient water to form an infinitely dilute solution. Infinitely dilute solution. Calculate the standard enthalpy change of hydration of the chloride ion. It may be helpful to draw an energy cycle, show all of your working. So we'll try to solve for this using an energy cycle. However, it's not necessary to use an energy cycle, right? The question is hinting that it may be helpful to draw an energy cycle, but you don't have to because the question doesn't specifically instruct you to do it. Okay, but we'll still draw an energy cycle here. Now, when we talk about the enthalpy change of hydration, right, here they've given us data on the enthalpy change of solution and the enthalpy change of hydration of calcium ions, right? So we have the enthalpy change of solution of calcium chloride, we have the enthalpy change of hydration of gaseous calcium ions, and we also have the lattice enthalpy of calcium chloride, right, which is negative 2237. Okay, so we can link these three. We can link the enthalpy change of hydration, the enthalpy change of solution, the lattice enthalpy, drawing an energy cycle. Okay, so we're going to start with calcium chloride solid. Okay, so CaCl2 solid. Right now we know that the lattice enthalpy is the energy released when the gaseous ions form 1 mole of this solid, right? So we have 2Cl minus gaseous. So this is negative 2237. That's the lattice enthalpy, right? We also know that the enthalpy change of solution over here is negative 83, right? It's negative 83. That's the enthalpy change when 1 mole of calcium chloride is dissolved, right, to form an aqueous solution. So that's negative 83. So if you go from calcium chloride solid to aqueous ions, right, so we have Ca2 plus aqueous and 2Cl minus aqueous, right, that is negative 83. That is negative 83. Okay, and then we want to find the enthalpy change of hydration of chloride. Now this enthalpy change over here from gaseous ions to aqueous ions is the enthalpy change of hydration. Now for calcium, that is negative 1650, right? That's given to us, negative 1650. And then we have 2 moles of chloride ions, right? We have 2 moles of chloride ions, so we have 2 times the hydration of chloride. We're going to call that X, that's our unknown, right? So what we can say here is that 2X minus 1650 is equal to minus 83 minus 2237. Okay, and we get X is equal to negative 335 kilojoules per mole. Okay, negative 335. So before I move on, I also want to mention that we can use the following expression to calculate the enthalpy change of hydration. Okay, the sum of the enthalpy changes of hydration, the sum of the enthalpy changes of hydration is equal to the lattice enthalpy plus the enthalpy change of solution. Okay, if you guys remember this formula or this expression, you can also use this to calculate the enthalpy change of hydration. Okay, if lattice enthalpy and enthalpy change of solution are given to you, or if, for example, you're given lattice enthalpy and enthalpy change of hydration, you can find the enthalpy change of solution, right? You can find any one of these values as long as the other values are given to you. So here the enthalpy change of hydration of the 2 moles of chloride ions was 2x, right? We had minus 1650 for calcium, and that was equal to the lattice enthalpy, that's minus 2237, plus the enthalpy change of solution, that was negative 83. And we can find the enthalpy change of hydration of chloride ions. Calcium fluoride can be synthesized directly from its elements. The value of the enthalpy change of formation of calcium fluoride is negative 1214 kilojoules per mole. Predict the sign of the entropy change for this synthesis. Explain your answer. So let's write down the equation for the enthalpy change of formation of calcium fluoride, right? We have elements in their standard state. So calcium solid, fluorine gas forming calcium fluoride solid, right? See, enthalpy change in 1 mole of a substance is produced in its standard state from the constituent elements in their standard states, right? So here we notice in the reactants we have 1 mole of fluorine gas, whereas in the products we have no gases, right? We have a decrease in the number of moles of gas. That means that there is a decrease in entropy or a decrease in disorder. So therefore the entropy change is negative. Okay, the entropy change is negative, and the reason why is because there is a decrease in the number of gas molecules, okay, or in the number of moles of gas. Use this value of enthalpy change of formation of calcium fluoride given in part E and your answer to E part 1 to predict how the feasibility for the synthesis will change with increasing temperature. So when we talk about feasibility, we're talking about the Gibbs free energy change. Okay, so let's first write down the expression, right? We know that delta G is equal to delta H minus T delta S, right? And we know that the enthalpy change of formation here is negative, right? And we know that this term over here, this minus T delta S term, will be the term that's affected by a change in temperature, right? Now, minus T delta S over here is positive, right? The reason why it's positive is because entropy change itself is negative. Because the entropy change is negative, T delta S is negative because temperature will always be positive. So if delta S is negative, T delta S is negative. That means minus T delta S is positive. So higher temperature means this term is more positive. Higher temperature means that this term becomes more positive. It becomes more positive as temperature increases. Becomes more positive as temperature increases, which means that delta G becomes more positive or less negative as temperature increases, which means that the feasibility decreases. More positive delta G means less feasible. Okay, the process is less feasible. So what we can say over here is that the delta S is negative. Therefore, minus T delta S is positive. Okay, when the temperature increases, minus T delta S, and therefore delta G becomes more positive, or we can say less negative, right? Hence feasibility decreases. Okay, hence feasibility decreases. So here we have question number 2. Part A says nitrogen monoxide reacts with ozone. The reaction is given over here. This reaction is first order with respect to both nitrogen monoxide and ozone. At 298 Kelvin, the rate constant K is equal to 11,500 per mole dm cube per second. Complete the rate equation for this reaction. The rate is equal to, so the rate equation is just an expression of the rate in terms of the rate constant and the concentrations of the reactant. So the rate equation is rate is equal to K, that's the rate constant, times the concentration of nitrogen monoxide to the power of 1, right? That's the order with respect to nitrogen monoxide. So that's the power to which the concentration is raised in the rate equation. So that's NO to the power of 1, and it's also first order with respect to ozone. A reaction is carried out in which the initial concentration of nitrogen monoxide and ozone are both 1.2 times 10 to the power of negative 6 mole per dm cube. Calculate the initial rate of this reaction, state its units. We're assuming that this reaction is taking place at 298 Kelvin. So over here we can say rate is equal to 11,500, right? That's the rate constant at 298 Kelvin. We're assuming that this reaction is taking place at 298 Kelvin. And the concentrations of nitrogen monoxide and ozone are both 1.2 times 10 to the power minus 6. So we have 1.20 into 10 to the power minus 6 squared. Okay, so we get the rate of reaction as 1.66 into 10 to the power of negative 8. Okay, and the units are concentration per unit time. Okay, those are the standard units for rate. Concentration per unit time. So moles per dm cube, that's concentration per unit time. So per second in this case, okay, because those are units for time. The reaction described in A part 2 is monitored over a period of time. Predict whether or not the graph of nitrogen monoxide, or the concentration of nitrogen monoxide against time under these conditions, shows that the reaction has a constant half-life. Explain your answer. Now, even though the reaction is first order with respect to nitrogen monoxide, okay, even though it's first order with respect to nitrogen monoxide, over time, it's not only the concentration of nitrogen monoxide that's affecting the rate. Now, the concentration of nitrogen monoxide will decrease over time. However, the concentration of ozone will also decrease over time, and that will also have an effect on the rate. So both of these reactants will have an effect on the rate over time, and therefore we can't determine the effect just because of nitrogen monoxide. If we were to use a large excess of ozone, then we can assume that the concentration of ozone doesn't change with time, and therefore we can monitor the effect of only nitrogen monoxide. But here we're not using a large excess of ozone. So the prediction here would be that the reaction would not have a constant half-life, okay, because it's not only nitrogen monoxide that's affecting the rate, okay. So the half-life will not be constant, okay. Half-life will not be constant, okay. And the reason why is because the reaction is not a first order reaction, okay. The overall order of the reaction is 2, okay, or it's a second order reaction overall, right. The way we can ensure that we get constant half-lives is by using a large excess of ozone, okay. So the overall order of the reaction is 2, or in other words we can say that the reaction is not an overall first order reaction. Nitrous oxide decomposes into its elements. At a high temperature, a small amount of platinum wire is added to a large amount of nitrous oxide. The reaction follows zero-order kinetics. The platinum wire behaves as a catalyst. Sketch a graph on the axes below of reaction rate against time for the catalyzed decomposition of N2O under these conditions. So when the question says the reaction follows zero-order kinetics, it means that the reaction is zero order with respect to the reactants. The reactant here being N2O, right? Nitrous oxide. Now, if it's zero order, it means that the concentration has no effect on the rate. So over time, even though the concentration is decreasing, the rate remains the same. We're going to have a constant rate, okay, over time. We're going to have a constant rate over time. Sketch a graph on the axis below of the concentration of nitrous oxide against time. The thing to keep in mind over here is that the rate, right, is the change in concentration per unit time, right? So the slope of a concentration time graph gives you the rate. Now, since the rate is constant for this reaction, that means that the slope of the concentration time graph is constant. And we know that a straight line has a constant slope. Okay, so since it's a zero order reaction, the concentration will obviously decrease. Since it's a reactant, it'll decrease linearly over time. Okay, it'll decrease linearly over time like this. So we'll get a straight line like this. Okay, so it'll be a straight line because the concentration decreases linearly over time. And the absolute value of the slope will be a constant, and that will be the rate. So we have a constant rate of reaction. Platinum behaves as a heterogeneous catalyst in this reaction. Describe the mode of action of a heterogeneous catalyst. Now, heterogeneous catalysts work on the basis of adsorption. Okay, so to understand this, let's look at an example, right? You know, the nitrogen and hydrogen in the Haber process react to form ammonia. Okay, and we use iron as a catalyst. Now what happens here is, if you think about the surface of the catalyst, here we have the iron catalyst. Okay, what happens is that the nitrogen molecules and the hydrogen molecules, they bond to the surface of the catalyst. Okay, that's called adsorption. Okay, so the first thing that happens here is that the reactants adsorb. Okay, they diffuse to and adsorb to the surface of the catalyst. Okay, diffuse to and adsorb. Okay, that's the key word here, adsorb. to the surface of the catalyst. Don't say absorb. Absorption means to soak in. Adsorption means to bond to the surface. Okay, so adsorb to the surface of the catalyst. Okay, and the effect that this has is because of this adsorption, the bonds in the reactants weaken. So when the bonds in the reactants weaken, right, it's easier for these bonds to break. It's easier for these bonds to break and react. Okay, it's easier for these bonds to break and react. So we can say that this weakens the bonds in the reactants, right, which obviously means that we've lowered the activation energy, right, lowers the activation energy, allowing the products to form, right. In this case, in this particular example, that will be ammonia, the one I've shown here, right. So what happens is that ammonia ends up forming, okay, ammonia ends up forming, and then at the end of it, what happens is that the ammonia desorbs or breaks away from the surface of the catalyst. Okay, so initially the ammonia is bonded to the surface and eventually it desorbs. That's the opposite of adsorbs. Okay, so ultimately what we have is the products desorb from the surface of the catalyst. From the surface of the catalyst. Okay. Okay, so the reactant diffuse and adsorb to the surface of the catalyst, weakens the bond in the reactants, allowing the products to form. So it allows the reaction to take place. Okay, so allows the reaction to take place and products to form. Okay, allows the reaction to take place and products to form, and then eventually the product is desorbed from the surface of the catalyst. Suggest a reason why this reaction has zero order kinetics when the amount of nitrous oxide is very large and the amount of platinum is small. Now the idea over here is, okay, let's say that I have a very, very small amount of platinum metal, okay, and I have a very, very large number, I have a very large number of gaseous molecules, okay, I have a very large number of gaseous molecules. Now over here, because we have a very large excess of nitrous oxide, okay, these molecules over here are nitrous oxide, because we have a very large excess of nitrous oxide, right, the platinum is really what's limiting the rate of the reaction. It's limiting the rate because there's not enough of it. So even if we increase the amount of nitrous oxide, it won't have any effect on the rate. Or even if we decrease it, it won't have any effect on the rate because there's still going to be enough for, there's still going to be more than enough for the platinum to work at full capacity. On the other hand, if we change the amount of platinum, it will affect the rate. So in other words, we don't have enough platinum for this reaction, which means that the platinum is working at full capacity, right? And the sites at which adsorption takes place is referred to as the active site. Okay, so what we can say over here is because we have very little platinum, we can say that all the active sites, okay, all the active sites on the catalyst surface, okay, on the surface of the catalyst, on the surface of the catalyst are occupied, right, i.e. the platinum is limiting the rate. Okay, so changing the amount of that will affect the rate of the reaction. However, changing the amount of nitrous oxide will not affect the rate. What you guys should understand is that changing the amount of the limiting substance affects the rate. Changing the amount of the substance in excess has no effect on the rate. If nitrous oxide is in such a large excess, okay, changing the amount of nitrous oxide will have no effect on the rate. So here we have question number 3. Data should be selected from table 3.1 in order to answer some parts of this question. So they've given us this table, okay, this table of standard reduction potentials or standard electrode potentials. An electrochemical cell can be constructed from a magnesium 2 plus Mg half cell and MnO4 minus Mn2 plus half cell. The standard cell potential of this cell can be calculated using the standard electrode potentials of the two half cells. Define standard electrode potential. Include details of the standard conditions used. The standard electrode potential is the EMF or a voltage of a half cell, Okay, it is the voltage of a half cell relative to the standard hydrogen electrode. Okay, relative to the standard hydrogen electrode. Okay, measured under standard conditions. Okay, and standard conditions, when we're talking about electrochemistry, when we're talking about cells, standard conditions are at 298 Kelvin, okay, atmospheric pressure, using 1 mole per dm cube solutions. Okay, so our electrolytes, okay, the solutions should be at a concentration of 1 mole per dm cube. Okay, each of the ions present in the equilibrium, or each of the ions present in both the half cells, should be at concentrations of 1 mole per dm cube. Complete the diagram below to show an electrochemical cell constructed from an Mg2 plus Mg half cell and MnO4 minus Mn2 plus half cell. Label your diagram. So let's first look at the magnesium half cell, right? The first question that I have is, what should the electrode be made of when we talk about the magnesium half cell? Now over here, because we have a metal in this redox equilibrium, the electrode should be that metal itself. Okay, so we're going to use magnesium for our electrode. Okay, we're going to use magnesium for our electrode. So here we have a magnesium electrode. Okay, we have a magnesium electrode. Okay, and our electrolyte over here, the only ion present in this equilibrium is Mg2 plus. We're going to have 1 mole per dm cube solution of Mg2 plus. Okay, and we're going to connect this to the other half cell using a wire. Okay, we're going to have a voltmeter. And now when we talk about the second half cell, the manganate 7 Mn2 plus half cell, what should the electrode be made of over here? Now over here, right, in this equilibrium, when we talk about MnO4 minus and Mn2 plus, talk about MnO4 minus and Mn2 plus, in this equilibrium, there's no metals present, right? There's no solid metals present. It's only ions. It's only ions. So the electrode has to be an inert metal. So we're going to use platinum. Okay, it has to be an inert substance. Okay, sometimes we use graphite as well. We're going to use platinum. Okay, and we have 3 different ions in this equilibrium. We have manganate 7 ions, we have H plus ions, and we have Mn2 plus ions. We're going to use 1 mole per dm cube solutions of each of these ions. Okay, so over here we're going to have a platinum electrode. Okay, we're going to have a platinum electrode, and we're going to use 1 mole per dm cube solutions of manganate 7, 1 mole per dm cube of Mn2 plus, and 1 mole per dm cube of H plus. In order to complete the circuit, okay, in order to complete the circuit, we're going to need a salt bridge. Okay, in order to complete the circuit, we're going to need a salt bridge. And we have to fully label this diagram. We have to fully label this diagram over here. Okay, so we have our salt bridge. Okay, that's usually a piece of filter paper soaked in saturated potassium nitrate. Okay, we have our voltmeter. Label the voltmeter. Okay, we've labeled the electrodes, and we've labeled the electrolytes. Use a positive sign and a negative sign to identify the polarity of each of the 2 electrodes in your diagram. Use an arrow and the symbol E to show the direction of electron flow in the external circuit. Now let's go back to the table over here. So the first question that I have is, if you look at these two half equations, right? Which of these two reactants, Mg2 plus or manganate 7, favor reduction more? Or for which of these is reduction more favorable? Look at the electrode potentials. Now, if you notice, the standard electrode potential for the reduction of manganate 7 is plus 1.52, right, to Mn2 plus, whereas the standard reduction potential for the reduction of Mg2 plus is minus 2.38. So we can say that the reduction of manganate 7 is more favorable. The reduction of manganate 7 is more favorable. That means that in this particular cell, this guy will be the oxidizing agent. It will undergo reduction. And that means that the equation that we have, the first equation that we have, the half equation for magnesium, will go in the reverse direction, right? Magnesium over here will undergo oxidation. It will be the reducing agent. Magnesium will undergo oxidation, it will be the reducing agent. So over here we can say that the magnesium is going to lose electrons and the manganate 7 will gain electrons. Again, this reaction is flowing from left to right and this reaction over here is going from right to left. So the magnesium is going to lose electrons, the manganate 7 is going to gain electrons. So the electrons are flowing from the magnesium half cell to the manganate half cell, right, or to the manganese half cell over here. So the flow of electrons over here will be from left to right. So what that means is this magnesium half cell, right, this electrode over here, this electrode is the negative electrode, right, and then this electrode here is the positive electrode. Okay, in a voltaic cell, electrons flow from the negative terminal to the positive terminal. So over here, right, this electrode is the anode, okay, because the magnesium is undergoing oxidation. Oxidation occurs at the anode, and then this electrode is the cathode, right, because the manganate 7 is being reduced here, okay, and reduction occurs at the cathode. Calculate the standard cell potential of this cell. Calculate the standard cell potential of this cell. Now, over here, right, we know that the manganate 7 is undergoing reduction, so that's plus 1.52, and the magnesium is undergoing oxidation, so that's the reverse reaction, so that will be plus 2.38, right? The manganate 7 is undergoing reduction, that's positive 1.52, and the magnesium is undergoing oxidation, that's the reverse reaction, so that will be plus 2.38. So we have plus 1.52 plus 2.38, or plus 1.52 minus 2.38, because we're reversing this reaction. So we have 1.52 minus 2.38, right? 1.52 plus 2.38. Okay, so we get positive 3.90 volts. Okay. Construct an equation for the cell reaction. So I'll just write down the half equations, right? Magnesium is undergoing oxidation to form Mg2 plus 2 electrons. That's the reverse of the standard reduction equation that they've shown. And MnO4 minus, right, is the oxidizing agent. It's undergoing reduction. It's the oxidizing agent. It's undergoing reduction. So we have Mn2 plus 4H2O. When we talk about a redox reaction, right, when we talk about the overall reaction, the electrons aren't shown in the overall reaction, right? So the gain and loss of electrons has to be balanced. So we can multiply the equation for magnesium by 5, and we can multiply the equation for manganate 7 by 2, right? So now we have 10 electrons being gained over here and 10 electrons being lost, right? So we can cancel out the electron, we just have to add up these two equations. So we have 5 mg, okay, we have 5 mg plus 2 MnO4 minus 5 mg plus 2 MnO4 minus plus 16H plus, okay, gives us 5 Mg2 plus, right, 5 Mg2 plus, and then we have 2 Mn2 plus and 8 H2O, okay, 4 times 2 is 8, so 2 Mn2 plus 8 H2O. Predict how the cell reaction will change, if at all, when the solution in the Mg2 plus Mg half cell is diluted by the addition of a large volume of water. Explain your answer. Now, if I add a very large amount of water to this half cell, okay, if I add a very large amount of water to this half cell over here, right, the concentration of Mg2 plus will decrease, right? The solution concentration will decrease because we're diluting this solution. Now, if I decrease the concentration of magnesium 2 plus, which direction does this equilibrium shift in? So decreasing the concentration of magnesium ions or diluting the solution will shift this equilibrium to the left, and the electrode potential will become more negative. Because the equilibrium is shifting to the left, the electrode potential will become more negative. It will become more negative. In other words, the reverse reaction will become more positive. So as an example, right, if this becomes negative 2.5, for example, the reduction potential, then the backward reaction becomes positive 2.5. So this will become even more favorable. The reverse reaction will become even more favorable. So if this value minus 2.38 is going to become more negative, or this plus 2.38 will become more positive, then what will happen to the cell reaction? So over here, if this value becomes more negative or this one becomes more positive, right, the reverse reaction, that means that the EMF of the cell becomes even more positive. The reaction becomes even more favorable. Now this reaction is already highly favorable because it has a very, very positive EMF, okay, the cell. So we're making this reaction even more favorable. So as far as the change is concerned, there is no change in the reaction. We have the same reaction taking place, right? We have the same reaction taking place. If anything, we're making it even more favorable. So there's no change in the reaction in the cell. It's the same reaction taking place, okay? So there's no change taking place, okay? There's no change, right? Because what happens over here is that when we dilute that half cell, right, the concentration of Mg2 plus decreases, right, making the electrode potential more negative for that half cell, more negative for the Mg2 plus Mg half cell, okay. You want to explain this further, it's because the equilibrium is shifting to the left, right? So the electrode potential becomes even more negative, which means that therefore the EMF of the cell, okay, becomes more positive. So the reaction becomes even more favorable. Okay. A molten magnesium salt is electrolyzed for 15 minutes by a constant current. 4.75 into 10 to the power of 22 magnesium atoms are produced at the cathode. Calculate the value of the current used. So the first thing we can do over here is that we can write down an equation for the reduction of magnesium ions at the cathode, right? Magnesium ions are gaining electrons at the cathode to form magnesium metal. And over here we're told that we have 4.75 into 10 to the power of 22 atoms of magnesium. So in order to find the current, okay, in order to find the current, we need to find how many electrons are being gained, okay, how many electrons are being gained. So we can find the number of electrons or we can find the moles of electrons, okay. If you want to find the moles of electrons, we first need to find the number of moles of magnesium. Now the number of moles, right, the number of moles is the total number of atoms divided by Avogadro's constant, right? Remember, the total number of atoms, capital N, is equal to the number of moles times Avogadro's constant, right? So we can say that the number of moles is equal to 4.75 into 10 to the power 22 divided by 6.02 into 10 to the power 23. So we get 0.07886 moles of magnesium atoms being deposited at the cathode. So then how many moles of electrons do we have? So for every 1 mole of magnesium being deposited, we have 2 moles of electrons being gained, right? So the number of moles of electrons will just be 2 times 0.07886. That means that the number of moles of electrons is 0.1577 moles. Okay, so that's the number of moles of electrons. Now, the number of moles of electrons can be related to the total charge, okay? The total charge Q is equal to the number of moles of electrons times Faraday's constant, right? And this is equal to the product of current and time, right? This is equal to the product of current and time. Now we know the number of moles of electrons, right? We know the number of moles of electrons as 0.1577, okay? Faraday's constant is 96,500 coulombs per mole, and this is equal to the current, which we want to find, times the time, which is 15 times 60 seconds. Okay, so NF is equal to IT, and then we can find that the current is equal to 16.9 amperes. Okay, so the current over here is 16.9. So that's our answer. Here we have question number 4, which says the value of the solubility product KSP of iron 3 hydroxide, FeOH3, is given by the following expression. And this KSP has a value of 2 times 10 to the power negative 39 mole to the power of 4 per dm to the power of 12. Okay, dm to the power of negative 12. Part 1 says calculate the solubility of iron 3 hydroxide in water. So we can just write down an equilibrium expression for the solubility of iron 3 hydroxide. Right, we have Fe3 plus and we have 3OH minus, right, aqueous. So on the left hand side we have the solid, on the right hand side we have the aqueous ions, and let's say that this guy has a solubility of X. So that means that when we talk about dissolving, let's say X moles dissolve. So the change in concentration is minus X, right? The change in concentration is minus X. In other words, X moles of this guy dissolve per decimeter cube. Then how many moles of Fe3 plus do we have? We'd have X moles of Fe3 plus, right? Because for every mole of iron 3 hydroxide, we get 1 mole of iron 3 plus, and we get 3x moles of hydroxide ions, right? Because for every 1 mole of this, we have 3 moles of hydroxide. Now again, the solubility is just X moles per decimeter cube. That's how it dissolves, and this is how many aqueous ions we get in solution. So initially we had 0, right? Initially we had 0 moles per decimeter cube of these ions, and then at equilibrium, we have X and 3x moles of Fe3 plus and hydroxide ions respectively. And we know the KSP expression, right? It's given to us. So Fe3 plus, that's X, concentration of Fe3 plus times the concentration of hydroxide, that's 3x cube, is equal to 2 times 10 to the power of negative 39. So over here we're going to get 27x to the power of 4 is equal to 2 times 10 to the power of negative 39, right? Which will give us x as 9.28 into 10 to the power of negative 11 moles per decimeter cube. So that's the solubility of iron 3 hydroxide. Okay, 9.28 into 10 to the power of negative 11 moles per decimeter cube. Calculate the solubility of iron 3 hydroxide in 0.01 moles per decimeter cube barium hydroxide. So now over here we have the same equilibrium, right? We have iron 3 hydroxide. We have iron 3 hydroxide forming Fe3 plus ions and hydroxide ions, okay, in aqueous solution. Now let's say that the solubility is Y, so we have a certain initial amount, right? And then let's say Y moles per decimeter cube dissolves. So there's a change in concentration of negative Y moles per decimeter cube dissolve. That's the solubility, that's Y. We get Y moles of Fe3 plus, and we get 3Y moles of hydroxide. However, we're going to ignore the amount of hydroxide ions from this. The reason why is because we can assume that all the hydroxide ions are coming from barium hydroxide, right? So we have a very large amount of hydroxide ions over here coming from barium hydroxide. So we can assume that this amount is negligible, right? This is called the common ion effect. And because there's very large concentration of hydroxide ions, so the equilibrium shifts to the left and we have a very low solubility of iron 3 hydroxide. So at equilibrium, we can say that we have Y moles of Fe3 plus per decimeter cube, okay, and then we can say that we have 0.02 moles per decimeter cube of 0.02 moles per decimeter cube of hydroxide ions, right? Because if we have 0.01 mole per decimeter cube of barium hydroxide, then this guy is going to give us 2 hydroxide ions, right? So if the concentration of this is 0.01, that means the concentration of hydroxide is 0.02. So now we can say that our KSP, that's 2 times 10 to the power of negative 39, is equal to the concentration of Fe3 plus, that's Y, times the concentration of hydroxide, that's 0.02 to the power of 3, and that gives us Y as 2.5 into 10 to the power of negative 34. So that is the solubility of iron 3 hydroxide in this solution of barium hydroxide. This is known as the common ion effect. Because of the presence of hydroxide ions from barium hydroxide, the solubility of iron 3 hydroxide decreases. Iron 3 hydroxide is less soluble in barium hydroxide aqueous than it is in pure water. Name this effect. This is known as the common ion effect. The numerical value of the Ka of HBrO is 2.00 into 10 to the power of negative 9. X is a solution of HBRO which contains 4 into 10 to the power negative 3 moles of HBRO in 100 cm cube of solution. In this solution, the following equilibrium is established in which there are two conjugate acid-base pairs. Define conjugate acid-base pair. Conjugate acid-base pair are two species, okay? They're two species that differ by a single proton, okay? By a single proton. Identify the two conjugate acid-base pairs shown in the equation above. So if you look at the left-hand side, what's the acid over here? So on the left-hand side, HBRO is the acid, right? It's a proton donor. H2O is accepting a proton, HBRO is losing a proton, right? So the acid on the left-hand side is HBRO, and its conjugate base is when HBRO loses a proton, right? So the conjugate base is BRO minus, okay? That's bromate 1. That's the bromate 1 ion. And then water is the base on the left-hand side. It's the base on the left-hand side. It's accepting a proton from HBRO, and the conjugate acid of water is H3O plus. So over here, H3O plus is the acid on the right-hand side. On the left-hand side, the base over here is H2O. Okay, so the conjugate base of HBRO is BRO minus, or we can say that the conjugate acid of BRO minus is HBRO. Similarly, we can say that H2O is the base and its conjugate acid is H3O plus, or we can say H3O plus is an acid and its conjugate base, when it loses a proton, it forms H2O. Calculate the pH of solution X. Show all of your working. Let's look at the information they've given us about solution X, right? This is the information that they've given us about solution X, right? Solution X is a solution of this weak acid, right? Solution of this weak acid over here. They've given us the value of Ka, and they've told us how much HBRO was dissolved in 100 cm cube of solution. So we first need to find out the concentration of the weak acid, right? HBRO is a weak acid. HBRO is a weak acid that forms H plus and BRO minus. Okay, this is a simplified equilibrium without H2O written, right? We need to first find the initial concentration. So the initial concentration of HBRO is the number of moles per unit volume. The number of moles is given to us as 4 into 10 to the power of negative 3. And the volume in decimeter cube is 0.1 decimeter cube. So we get the concentration as 0.04 moles per decimeter cube. That's the initial concentration of the acid. Okay, that's the initial concentration of the acid. So we can say that the initial concentration of the acid is 0.04. And we can say that, let's say, X moles of the acid ionize per decimeter cube, which means we get X moles of this and X moles of this. So at equilibrium, we can assume that our final concentration of acid is the same as the initial concentration. Because it's a weak acid, it barely ionizes, right? So we have 0.04 mole per decimeter cube at equilibrium of this, and we have X of this and X of this. We know the Ka is equal to the concentration of H plus times the concentration of BRO minus divided by the concentration of HBRO, right? And this is basically X squared divided by 0.04 is equal to the Ka, which is 2 into 10 to the power of negative 9, right? And this gives us a value of X as, what? We get X is 8.94 into 10 to the power of negative 6 moles per decimeter cube. Okay. Moles per decimeter cube, right? And this over here, okay, is the concentration of H plus. Okay, this is the concentration of H plus, right? So for the pH, we can just say the pH is equal to the minus log of this, right? So minus log of the concentration of H plus, and we get the pH as 5.05. Okay, so that's our answer. The pH is 5.05. A solution containing 2 into 10 to the power of negative 3 moles of sodium hydroxide is added to solution X. A buffer solution is formed. Calculate the pH of this buffer solution. The solution X had 4 into 10 to the power of negative 3 moles of HBRO. Okay, so what happens is that the HBRO Okay, the HBRO reacts with the NaOH, right, to form salt and water. So NaBRO and H2O. Initially, we had 0.004 moles of this, and 0.002 moles of NaOH were added, right, 2 into 10 to the power of negative 3 moles. And what happens is that all the NaOH reacts, and 0.002 moles of the HBRO react. So we're left with 0.002 moles of HBRO, and we also end up making 0.002 moles of NaBRO. Okay, we also end up making 0.002 moles of NaBRO. So now what we have is, we have a solution of a weak acid and its conjugate base, right? So we can say that the Ka is equal to the concentration of H plus times the concentration of BRO minus divided by the concentration of HBRO. But here we can assume that all the bromate ions are coming from the conjugate base. Okay, and since we have equal amounts of the acid and the conjugate base, right, since we have equal amounts of the acid and the conjugate base, right, the numerator and the denominator, the BRO minus and the HBRO will cancel each other out. So the Ka is equal to H plus, which means that the concentration of H plus is simply the Ka, which is 2 into 10 to the power of negative 9. Right, 2 into 10 to the power of negative 9. That's the Ka, and therefore the pH is just the minus log of H plus, which is equal to 8.70. So over here, when the sodium hydroxide solution is added, the volume of the solution changes. Okay, we don't really care about the concentrations of these two, because we know that the number of moles for these two are the same. That means that concentration is the same, and therefore these guys will cancel each other out, because they're both in the same solution. So same number of moles would mean the same concentration, since we're dividing by the same volume for both of them. So from this expression, we can deduce that the Ka is just the concentration of H plus, and then we can find the pH. So here we have question number 5. It says copper is a transition element. It forms a wide variety of compounds. Part A says define transition element. A transition element is a D block element. It's a D block element that forms at least one stable ion, that forms at least one stable ion with partially filled D subshell. Okay, with the partially filled D subshell or with partially filled D orbitals. Okay, with the partially filled D subshell or partially filled D orbitals. Okay, if the orbitals are partially filled, the D subshell will also be partially filled. Okay, an aqueous solution of copper 2 sulfate CuSO4 contains copper 2 hexa-aqua complex ions. Okay, that's CuH2O6 2+. If an excess of concentrated hydrochloric acid is added to the solution, a ligand exchange reaction occurs and copper 2 tetrachloride complex ions are formed. Complete table 5.1 to state the geometry, the coordination number of copper, and one bond angle in each of the two complex ions. So this complex, okay, the copper 2 hexa-aqua complex is an octahedral complex, right? It's a 6-coordinate complex. It's a 6-coordinate complex with bond angles of 90 degrees. Okay, and then the copper tetrachloride, copper 2 tetrachloride, is a tetrahedral complex. It's a tetrahedral complex. Coordination number is 4 and bond angles are 109.5 degrees. In an isolated copper 2 plus ion, the d orbitals are all degenerate. In a complex ion such as copper 2 hexa-aqua, the d orbitals are non-degenerate. Define degenerate and non-degenerate in this context. So in an isolated ion, all the d orbitals are at the same energy. Okay, that's what we mean by degenerate d orbitals. So over here we would say that degenerate just means at the same energy. Okay. And in a complex, what happens is the d orbitals are split into groups that have different energies. So non-degenerate simply means that they have different energies, okay, or not the same energy, okay, at different energies. Explain why the solutions of the two complex ions in table 5.1 are different colors. So when a complex ion forms, right, the d orbitals are split into different energies, and that difference in energy corresponds to a certain frequency of visible light that is absorbed. For different complexes, the delta E is going to be different. The delta E is different, okay? Therefore, different frequencies, okay, or wavelengths of visible light are absorbed, okay? Of visible light are absorbed, okay, which means that different complementary colors are observed. Different complementary colors are observed. Copper 2 plus forms a complex ion containing water molecules and ethane dioate ions as ligands. The formula of the complex ion is CuC2O4 twice, H2O twice, 2 minus. The ethane dioate ion is a bidentate ligand. Explain what is meant by bidentate. So a bidentate ligand is a ligand that donates two lone pairs of electrons to form two dative bonds. Okay, so it donates two lone pairs of electrons, okay, to form two dative bonds. Okay. Specifically, a species that donates two lone pairs of electrons to form two dative bonds. There are three stereoisomers with the formula CuC2O4 twice, H2O twice, 2 minus. Complete the three-dimensional diagrams to show these three stereoisomers. This is the structure of C2O4 2 minus, okay? It's ethane dioate. So over here, okay, what we're gonna have is we can have the two water molecules. Directly opposite each other like this, right? That would be the trans isomer, and then the two bidentate ligands would be like this, right? So we have this, and then what we have is we have an oxygen bonded to a C double bond O, bonded to a C double bond O, bonded to an oxygen like this, and then we have the same thing on the other side. An oxygen bonded to a C double bond O, bonded to a C double bond O, bonded to an oxygen like this, right? So this is the trans isomer, and then we can also have the cis isomer, right? Now for the cis isomer, the two water molecules will be at 90 degrees to each other. Okay, the two water molecules will be at 90 degrees to each other, like this. And then we're going to have the two bidentate ligands again. So we have oxygen bonded to a C double bond O, bonded to a C double bond O, bonded to an oxygen, right, like this. And then we have the same thing over here. We have an oxygen bonded to a C double bond O, bonded to a C double bond O, bonded to an oxygen like this. So this is one of the cis isomers, okay? And over here, notice the trans isomer is symmetric, whereas the cis isomer is asymmetric, so it exhibits optical isomerism. So we also have the optical isomer of this cis isomer that I've drawn. So in the optical isomer, all we're going to do is we're just going to reverse the arrangements, right? So over here, I've shown the water molecule on the right. So over here, I'm going to show it on the left. Okay. So what we're going to have over here is I'm going to have the same thing, but with the opposite arrangement of water molecules. Okay, so we have H2O, and then we have the bidentate ligand, C double bond O, C double bond O, and then the oxygen, and then oxygen, C double bond O, C double bond O, and then the oxygen. So these two are optical isomers, okay? They're optical isomers. They're non-superimposable mirror images of each other. Use your answer to C part 2 to answer this question. Stereoisomers 1, 2, and 3 show two different types of isomerism. Name these two types of isomerism. For each type of isomerism, identify the pair of stereoisomers that demonstrate this isomerism. So we have geometric isomerism, right? Geometric isomerism is shown by isomers 1 and 2, or we can say 1 and 3, right? Because 1 is the trans isomer and 2 and 3 are both cis isomers, so 1 and 2 or 1 and 3, right? Those are cis trans isomers or geometric isomers. We'll just say 1 and 2. And then we have optical isomerism, which is shown by isomers 2 and 3, right? Those are the two cis isomers that are non-superimposable mirror images of each other. Part D says a solution contains 3.70 grams of this salt dissolved in 100 cm cube of solution. A 25 cm cube sample of this solution is warmed and then oxidized by 0.01 moles per decimeter cube acidified potassium manganate 7. The equation for the redox reaction is shown. Calculate the minimum volume of 0.01 moles per decimeter cube acidified potassium manganate 7 needed to oxidize all of the ethane dioate ions in the 25 centimeter cube sample. Show all your working. So this reaction, right, this reaction that's taking place is with the 25 cm cube sample, right? And we've been given the initial mass of the salt that was dissolved in 100 cm cube of the solution, from which we took 25 cm cube. So what's the first thing we would do here? What information is given to us that we can first use? So over here, since we've been given the mass of the salt, initially and the MR, right, we can first calculate the number of moles of salt. Okay, the number of moles of salt is equal to the mass divided by the molar mass, which is 0.370 divided by 321.5, which is equal to 0.0115 moles of salt. In this reaction here, we have ethanoate reacting with manganate 7. Now that we have the number of moles of salt, we can find the number of moles of ethanoate ions, right, in the original 100 cm cube solution. Every 1 unit of the salt, has 2 ethanoate ions, right? Every 1 unit of the salt has 2 ethanoate ions. For 1 mole of salt, we'll have 2 moles of ethanoate. If we have 0.0115 moles of the salt, we have 2 times 0.0115 moles of ethanoate ions. That's 0.0230 moles of ethanoate ions in 100 cm cube. And we take 1/4 of that solution for the reaction. So in 25 cm cube, we have, so this implies that we have 0.0230 divided by 4 moles of ethanoate ions in the 25 cm cube sample that we took for the reaction. Okay, again, because 100 cm cube solution had this many moles, and we took 1/4 of that solution to react with manganate 7. So now we know that in this reaction we had 5.75 into 10 to the power -3 moles of ethanoate ions, or 0.00575. So then, since we want to find the volume of manganate 7 solution needed, we can now find the number of moles of manganate, right, using this ratio in the equation of 5:2, right? So we know that for every 5 moles of ethanoate ions, we're going to need 2 moles of manganate 7 ions. And since we have 0.00575 moles of this, right, let's say we need n moles of manganate ions, which implies that the number of moles of manganate ions needed for the reaction are, we just cross multiply and we get 0.00230 moles of manganate 7. We want to find the volume. You know, the number of moles is equal to the concentration times the volume. Right? The number of moles is 0.00230 moles. The concentration is 0.01 moles per decimeter cube. And the volume is what we have to find, which gives us a volume of 0.23 decimeter cube. We want the volume in centimeter cube, so we multiply this by 1,000. Multiply this by 1,000, we get 230 centimeter cube. Okay. Copper 2 nitrate and barium nitrate both decompose when heated. Copper 2 nitrate decomposes at a lower temperature than barium nitrate. Suggest a reason for this difference. Explain your answer. If you remember from group 2, right? When we go down the group, when you go down the group, the thermal stability increases. Okay, the thermal stability increases down the group. Okay, the reason why is because the cations get larger, so the charge density decreases, so the polarizing power decreases. Okay, so the anion is not distorted as much. So magnesium ions will polarize the anion more because they're smaller, so they have greater charge density. Same charge, but smaller size. Okay, so if they're saying copper 2 nitrate decomposes at a lower temperature than barium nitrate, it means that copper 2 nitrate is less thermally stable, or barium nitrate is more thermally stable, which means that the copper 2 plus ion, okay, the copper 2 plus ion has a smaller ionic radius, than the barium 2 plus ion. Therefore, we can say that the copper 2 plus ion has a greater charge density, right? Because it has the same charge, but smaller size, so greater charge density and polarizing power, charge density and polarizing power, and causes greater polarization of the nitrate ion. Okay, so a lower temperature is needed for the decomposition of copper 2 nitrate. Okay, or you can say that copper 2 nitrate is less thermally stable. Okay, so here we have question number 6, which says an aqueous solution of cobalt 2 chloride is a pink color due to the presence of cobalt 2 hexaaqua complex ions. A part 1 says complete table 6.1 to describe what is observed when the named reagent is added to an aqueous solution of cobalt 2 chloride. So the question is asking, when each of these two reagents is added to cobalt 2 chloride, right, what is the color of the cobalt product and what is the state of the cobalt containing product? So if sodium hydroxide is added to cobalt 2 chloride, what do we get? So here we have a precipitation reaction taking place where we form cobalt 2 hydroxide, okay, and that is a blue precipitate. Okay, that is a blue, we get a blue precipitate. Okay, so it's a blue solid. Now you can write pink because this precipitate, okay, it eventually turns pink, but initially it appears as a blue precipitate which then turns pink. Okay, that's why you will see pink written sometimes, but immediately what you see forming is a blue precipitate. When we add excess of concentrated HCl, right, we already have a cobalt 2 chloride solution. Okay, and what we're going to do is by increasing the amount of chloride ions, we're going to get more of cobalt 2 chloride. Okay, we're going to get more of cobalt 2 chloride, and cobalt 2 chloride is a blue solution. Okay, it's a blue solution. Okay, and the state is aqueous. Right, it's a solution. Write an equation for the reaction between cobalt hexaaqua ions and sodium hydroxide aqueous. So here we just have CO H2O6 2 plus reacting with hydroxide ions to form CO OH twice H2O4. Okay, we get a neutral precipitate. And we get 2H2O. Okay, we get 2H2O. You can write down the simplified equation, okay, where we just have COOH twice, and then we'll have 6H2O. Write an equation for the reaction between the hexaaqua ions and an excess of concentrated HCl. Here we have a ligand exchange reaction. So cobalt hexaaqua, cobalt 2 hexaaqua, COH2O6 2 plus reacts with chloride ions to form a tetrahedral complex, okay, to form a tetrahedral complex of cobalt tetrachloride, okay, cobalt 2 tetrachloride, COCl4 2 minus, and we get 6H2O. B part 1 says define stability constant. the stability constant is the equilibrium constant. Okay, it's the equilibrium constant for the formation of a complex, okay, from its constituent ions, or molecules or even atoms, okay, in a given solvent. Write an expression for the stability constant of the cobalt hexaamine complex, the cobalt 2 hexaamine, okay, CONH3 6 2 plus. So you can write down the simplified stability constant, okay. We have this complex ion being formed, CONH3 6 2 plus, from its constituent ions or molecules. So we have cobalt 2 plus concentration, right, and we have 6 ammonias, right? So we have NH3 to the power of 6, concentration of ammonia to the power of 6. This ion over here is just the hexa aqua complex, okay? So you can also write COH2O6 2 plus, okay? But in its simplified form, you can also just say CO2 plus. Give the units of the stability constant of this complex ion. So for the units over here, we have concentration in the numerator divided by concentration to the power of 7, right? 1 plus 6, 7 in the denominator. So we have concentration to the power of negative 6, right? So that is mole to the power of negative 6 dm to the power of 18, right? Again, this is just moles per dm cube. This is just moles per dm cube to the power of negative 6. Okay, so we get per mole to the power of 6, mole to the power of negative 6, dm to the power of 18. The numerical value of the stability constant for this complex is 7.7 into 10 to the power of 4. In an aqueous solution, the concentration of the cobalt 2 hexaamine complex is 0.074 moles per decimeter cube, and the concentration of ammonia is 0.48 moles per decimeter cube. Calculate the concentration of the cobalt 2 hexa aqua complex in this solution. So again, this complex over here, right, is just CO2 plus written in the simpler form, right? So CO2 plus is just this complex over here. So let's just say that the concentration of this is X, right? So what we have over here is for the hexaamine complex, we have a concentration of 0.074, so 0.074 in the numerator, 0.074 divided by the concentration of ammonia, which is 0.48 to the power of 6 times X, right? That's the concentration we want to find, and this is equal to the stability constant, which is 7.7 into 10 to the power of 4, which is just 77,000. So this gives us a value of X as 7.86 into 10 to the power of negative 5 moles per decimeter cube. Okay, so that's the concentration of cobalt 2 plus ions, okay, or cobalt 2 hexa aqua ions in solution. So 7.86 into 10 to the power of negative 5. So here we have question number 7. Part A says the structural and displayed formula of 3 aromatic compounds A, B, and C are shown in figure 7.1. Compare the relative acidities of A, B, and C. Now, first of all, A and C have carboxylic acid groups, whereas compound B is a phenol, right? We should know that carboxylic acids are more acidic, so we know that B has to be the least acidic, okay? B has to be the least acidic. Now, between A and C, right, C is more acidic because of the presence of the electron withdrawing chlorine atom. Because this chlorine is present, it withdraws electron density away from the OH bond. Okay, it withdraws electron density away from the OH bond, which makes this OH bond weaker and makes it easier for the carboxylic acid to ionize. So C is going to be the most acidic, followed by A, followed by B. So to explain this, the first thing we would say over here is that carboxylic acids are stronger acids than phenols, right, due to the presence of the due to the presence of the C double bond O. The electronegative oxygen atom withdraws electron density away from the OH bond, right, making it weaker, and therefore it is easier for H plus ions to form. Okay. You can also talk about the stability of the conjugate base. Right? The electronegative oxygen atom, what it does is, because it withdraws electron density, it makes the conjugate base more stable. And more stable conjugate base means stronger acid. Okay, and then we also have to explain the effect that the chlorine has, right? So the presence of the electronegative chlorine atom further weakens the OH bond. Okay, electronegative chlorine atom further weakens the OH bond by withdrawing electron density away from the OH bond. Methylbenzene can be made from benzene by an electrophilic substitution reaction. Identify a compound that reacts with benzene to form methylbenzene. Identify the catalyst used. So if you want to make methylbenzene from benzene, right, what we're doing here is this, right? We're simply making methylbenzene from benzene, right? So we're just substituting a methyl group. So what we're going to use here is we're going to use CH3Cl. Okay. If you want a CH3 group to bond to the benzene ring, we're going to use a chloroalkane, where that CH3 was initially bonded to a chlorine. Okay. And the catalyst that we use is AlCl3. Okay. And usually we heat this. Okay. So the compound is going to be CH3Cl, or you can say chloromethane. Okay. You can name it as well. And the catalyst is AlCl3. We can use FeCl3 as a catalyst as well. The first step in this reaction is the generation of the CH3 plus electrophile. Write an equation for the reaction that generates this electrophile. So what happens here is that the CH3Cl reacts with the catalyst, the AlCl3, to form the electrophile CH3 plus and AlCl4 minus. Describe the mechanism for the reaction between benzene and the electrophile. Include all relevant curly arrows and charges. So in the first step, okay, what we have is we have the donation of a pair of electrons from the ring, okay, from the ring to the electrophile, and we end up getting a carbocation intermediate, right? We end up getting a carbocation intermediate like this. And then the second step of this mechanism, the CH bond breaks and the electrons from the CH bond go back into the ring, and we end up getting methylbenzene. So we end up getting methylbenzene and H plus. Identify a suitable reagent to oxidize methylbenzene to benzoic acid. Write an equation for this reaction using O to represent one atom of oxygen from the oxidizing agent. So for this reaction, we're going to use alkaline KMnO4, okay, and heat. So we're going to use hot alkaline, okay, alkaline manganate 7 or potassium manganate 7 KMnO4, followed by H plus. Yeah, because in alkaline condition we get the salt of the acid, so we're going to follow it up with H plus so that we get the carboxylic acid. And the equation for this, we just write down the overall equation. We have C6H5CH3 forming C6H5COOH. Now notice over here in the reactants we have 3 hydrogens here in the methyl group. Here we just have 1 hydrogen. So what other product do you think we'd get? So the other product that we get over here is H2O. Okay, that's where the remaining two hydrogens go. So what we've done here is we have a total of 3 oxygens, right? 2 of them being added to this carbon, and then 1 more oxygen that's taking away the 2 hydrogens. So we're going to have 3 oxygens. Methylbenzene and benzoic acid are both nitrated with a mixture of concentrated nitric acid and sulfuric acid to give mononitrated products. The structural formula of these products are CH3C6H4NO2 and CO2H or HOOC C6H4NO2 respectively. Draw the structures of these two products. Now we talk about methylbenzene, right? When methylbenzene is nitrated, which position would the nitro group go to? Now remember that if we have a certain group present on the benzene ring, that determines the position of any new substituents. The methyl group is a 2,4 directing group. So when methylbenzene is nitrated, the nitro group will go to either the 2 position or the 4 position. Okay, so let's just say it goes to the 2 position over here. And then when we talk about benzoic acid, right, the carboxylic acid group is a 3 directing group. So if we nitrate this to get nitrobenzoic acid, we're going to get 3 nitrobenzoic acid. Okay, the nitro group will go on position 3. Again, this group will determine where the nitro group will go. Okay, so it's a 3 directing group, hence we get 3 nitrobenzoic acid. A reaction scheme is shown in figure 7.2. Describe the reagents and conditions to produce this salt. Okay, this is a diazonium salt from this phenylamine in reaction 2. So for reaction 2, this is a diazotization reaction. Okay, diazotization, when phenylamine is converted into a diazonium salt. So for that, we're going to use NaNO2 and HCl. Okay. Sometimes you will see HNO2 being used, but what happens here is that NaNO2 and HCl react to form HNO2, okay, which then reacts with the phenylamine, and we have to ensure that the temperature is less than 10 degrees Celsius. Okay, so the conditions over here, the temperature has to be below 10 degrees Celsius because this diazonium salt is unstable. Okay, it will decompose at a higher temperature. Describe how CH3C6H4OH, the phenol, can be produced from this diazonium salt in reaction 3. So the diazonium salt can get hydrolyzed by water to form phenol. Okay, because it's unstable at any temperature above 10 degrees Celsius, it will get hydrolyzed to form a phenol. Okay, so over here, you can just say warm, okay, in water. Okay, warm in water. At any temperature above 10 degrees Celsius, this will actually happen. Okay, so warm in water. Draw the structure of the dye molecule formed when this salt and CH3C6H4OH react together in reaction 4. Describe the conditions for this reaction. What happens over here is this, right? We have the diazonium salt, N triple bond N plus and then Cl minus, and this guy is reacting with a phenol. Okay, this guy is reacting with a phenol. Now we don't really care about the position of the methyl group. Okay, it could be at any position. Let's just say it's at this position. We don't actually know the position of the CH3 group. Right? We don't know the position of the CH3 group. What ends up happening is that the nitrogens, right, the N triple bond N becomes an N double bond N, right, and it bonds. Okay, it bonds to the phenol, right? So again, we don't know the actual positions of the groups over here, but I'm just showing it like this, right? And we can just write down the structure like this. Okay, so this is the product that we get. Again, this nitrogen over here, okay, will end up bonding to this carbon. So this nitrogen will end up bonding to this carbon. So this is the product that we get. Okay, this is the product that we get. So what we get is we get CH3 C6H4, okay, bonded to an N double bond N, okay, C6H4 CH3 C6H4 N double bond N, and then, right, this guy is a C6H3, okay, C6H3 now, C6H3 bonded to the benzene ring, that has a CH3 group and an OH group. Okay, so I've written this down like this. Okay, so this would be an acceptable answer as well. Okay, what you should know is that one of the hydrogens over here in the phenol is substituted for by the nitrogen. Okay, and we have to clearly show the azo group. Okay, this is the azo dye that we're forming, right? This is an azo dye or an azo compound. And the conditions for this, again, we want to ensure that we use a low temperature, okay, because the diazonium salt is heat sensitive and it's going to be carried out in alkaline conditions. So we say aqueous alkali. So here we have question number 8, which says when answering this question, it should be assumed that together all the hydrogen atoms in a benzene ring result in a single unsplit peak at 7.2 parts per million in the proton NMR spectrum. Part A says identify all the chiral carbon atoms on the structures above. Label each chiral carbon atom with an asterisk. So we look at compound P, benzene ring, and CO. These are all sp2 carbons, right? And then this CH over here has two methyl groups, so there's no chiral carbons here. There's no chiral carbons here either. Again, CO and the benzene carbons aren't chiral. And then CH2, CH2, CH3. No chiral carbons here. Okay, we do have a chiral carbon over here in compound T, right? This carbon over here, right? This carbon is bonded to a hydrogen, a C6H5, a CH3, and a COCH3. So this is a chiral carbon, and there's no chiral carbons over here. So there's only one chiral carbon. Okay. The proton NMR spectrum of one of these 5 isomers P, Q, R, S, or T is shown in figure 8.1. Identify which of the compounds P, Q, R, S, or T gives this spectrum. Draw the displayed formula of the compound you have identified. Identify the protons responsible for the peaks at 3.7 parts per million, 2.5 parts per million, 1.0 parts per million on the structure you have drawn. So first of all, in this spectrum, we see this triplet quartet, which suggests which group is present. Whenever we see a triplet quartet splitting pattern, okay, we should know that an ethyl group is present. Okay, a CH3, CH2 is definitely present. The reason why is because the CH3 protons, the 3 protons are split into a triplet by the neighboring 2. So the CH3 protons are split into a triplet by the neighboring 2. And the CH2 protons are split into a quartet by the neighboring 3. So over here, this triplet is because of the CH3 protons being split into 3 by the neighboring 2. Remember, 2 plus 1, the neighboring 2 plus 1. So that's 3. This peak is split into 3. And then these two are split into 4 by the neighboring 3. Neighboring 3, so splitting pattern is 3 plus 1, which is 4. So over here, where do we have a CH3CH2? This ethyl group is present only in compounds Q and R. So that narrows down our choices, right? This has to be compound Q or R. It has to be compound Q or R because only these two compounds have a CH3CH2. Now over here, the question has told us that the peak at 7.2 is because of the benzene protons, right? The peak at 7.2 is because of the benzene protons, right? Those are the C6H5 over here. That's the peak at 7.2. That's the peak at 7.2, right? And this other peak over here that's left, right? We've already identified that we have a CH3, CH2 in both, right? But then this peak over here is a singlet, so it's not being split. Now the CH2 here has neighboring protons. This CH2 should be a triplet. This CH2 should be a triplet because the neighboring carbon has 2, whereas the CH2 here is a singlet. So it must be this one. Okay, because this carbon is bonded to the benzene carbon that has no protons on it, so it's not being split. So this proton here will be a singlet. Okay, so this guy over here is this peak. So that means that we have compound R over here, okay, not compound Q. Okay, so the compound responsible for this spectrum is compound R. We have to draw the displayed formula of compound R. Okay, for the displayed formula of compound R, we have C6H5 CH2 CO CH2 CH3. So C6H5, and then we have a CH2 We have a CH2 bonded to a CO, CH2, CH3, bonded to a CO, CH2, CH3. We have to draw the displayed formula. CO, CH2, CH3. Okay. So now we have to identify which of the protons are responsible for each of these peaks, right? So we already said that the CH3 protons are the ones being split into a triplet at 1.0 parts per million, right? So the CH3 protons, right, they have a split of 1.0 parts per million, right? That's HA. The CH2 protons over here are being split into a quartet, by the neighboring three, at around 2.5 parts per million. Okay. And then we have the CH2 singlet at 3.7. So CH2 singlet at 3.7 parts per million. Okay, 3.7 parts per million. Name the splitting pattern at delta is equal to 3.7 parts per million. Explain why it has the splitting pattern. So at 3.7 we have a singlet. Okay, so that's the splitting pattern, the name of the splitting pattern. And the reason we have a singlet is because there are no hydrogens on the neighboring carbon atoms. Choose from the letters P, Q, R, S, and T to identify the two compounds that each have a doublet in the proton NMR spectrum. So which of these two compounds will have a doublet? In other words, a proton where the neighboring carbon has one proton. The neighboring carbon has one proton, so we see a 1 plus 1, 2 splitting pattern, a doublet. So we have a CH. Which of these two have a CH? That will be compounds P and T, right? P and T. So in P, these two CH3s will be split into a doublet, right, by the neighboring one. And then over here, this CH3 will be a doublet because of the neighboring carbon having one proton. So that's going to be P and T. The compound with only 3 peaks in the proton NMR spectrum. So which of these compounds only has 3 different types of protons or 3 non-identical hydrogen atoms? That's compound P. Remember, we're treating all the benzene protons as one type, right? Then we have the CH proton, that's the second type. And these two CH3s are identical, so that's the third type of proton. All 6 of these protons are identical. We only have 3 different proton environments or 3 non-identical protons. So that will be compound P. Suggest a suitable solvent that should be used for obtaining the spectrum shown in figure 8.1. That's just CdCl3. Okay, that's deuterated trichloromethane. Okay, you can also use tetrachloromethane, CCl4. The proton NMR spectrum of compound T is compared in the presence of D2O and in the absence of D2O. Describe any difference between the two spectra. Explain your answer. So D2O reacts with labile protons. Okay, D2O is an NH or an OH proton. Okay, these guys undergo proton exchange. Where the hydrogen 1 is replaced by a deuterium. Now, does compound T have an NH or an OH proton? It doesn't have an NH or an OH proton, so therefore there will be no difference in the spectra. Okay, there will be no difference in the spectra. So for part E, we can say that there will be no difference. Okay, there will be no difference in the two spectra. Okay, no difference in the two spectra because there are no labile protons. Okay, no labile protons. Again, those are NH or OH protons. Okay, NH or OH protons, and therefore there is no proton exchange. Okay, there is no proton exchange. Complete table 8.1 below to give the number of peaks in the carbon-13 NMR spectra of each compound. When we talk about carbon-13 NMR, we're trying to identify the number of non-identical carbon atoms, or the number of different carbon-13 environments, right? That'll be the number of peaks. That'll be the number of peaks. So in the first compound, we have a line of symmetry here, right? So we have, this is one carbon atom that we have, the CH3 carbon, then the CH2 carbon is the other one, right? The second one, then we have a third one here, and then these two are identical, that's carbon number 4, right? So this is a line of symmetry. Then we have carbon number 5, and then we have this carbon, that's carbon number 6. So we have 6 peaks, okay, because we have 6 carbon-13 environments. If you look at the compound on the right, the top right, right, we have a line of symmetry here, right? So we have one carbon here, then these two are identical, these two are identical, that's 3, then 4, and then 5. So we have 5 peaks. Then over here, we have again a line of symmetry right here, right? We have a line of symmetry right here. So these two are identical, that's 1, 2, and then 3, and then 4. So we have 4 different peaks. And then for the last compound, right, we have 2 lines of symmetry. We have a line of symmetry here and here. So these two are identical, right? These two are identical. And then all 4 of these are identical, right? These two are identical. And then because there's a line of symmetry horizontally as well, right, these two would also be identical to carbon number 3. So we only have 3 different peaks. So here we have question number 9, which says tyrosine and lysine, shown in figure 9.1, are naturally occurring amino acids found in proteins. The isoelectric point of lysine is 9.47. That's the pH at which lysine is neutral. Okay, it has no net charge. Draw the structure of lysine at the stated pH in the boxes below. So if the pH is below the isoelectric point at a pH of 7, what charge would lysine have? So if the pH is below the isoelectric point, right, at the isoelectric point is neutral. At a lower pH, we have an excess of H plus ions, which means that lysine will be positive. Okay, the amine group will gain a proton. Doesn't matter where we show it. It could be this NH2 becoming an NH3 plus or this one. Okay, either one of them. Okay, so at pH 7, okay, at pH 7, what we're going to have is we're going to have lysine. Okay, nothing happens to the acid group, so the CO2H remains the same, and then the NH2 becomes an NH3 plus. Okay, the NH2 becomes an NH3 plus, and then we have 1, 2, 3, 4, and then we have an NH2. Okay, at a pH of 9.47, it's neutral, so it exists in its Zwitter ionic form. Okay, it exists in its Zwitter ionic form. So we have NH2 here, and we have 1, 2, 3, and then 4, and then we have an NH3 plus. Okay, and then we have a CO2 minus. Okay, it's neutral. And at a pH of 12, that's above the isoelectric point, we have an excess of hydroxide ions, which means that the acid group loses its proton. Okay, the acid group loses its proton. So what we have is we have the NH2, and then we have 1, 2, 3, and then 4, right? And then what we have over here is we have an NH2, we have an NH2, and then we have a CO2 minus. So it has a negative charge, okay, because the pH is above the isoelectric point. Okay. When ethanoic acid is treated with PCl5, product D is formed. When D is added to tyrosine, 2 different isomeric products E and F are formed. E has an ester linkage, F does not. Draw the structures of D, E, and F. Now, when a carboxylic acid reacts with PCl5, we get an acyl chloride. So here we'll get ethanoyl chloride. Okay, we get ethanoyl chloride. So we have a 2-carbon acyl chloride. Okay, so the OH group is replaced by a chlorine. So this is ethanoyl chloride. Now E and F are formed when D reacts with tyrosine. Okay, so let's look at the structure of tyrosine. Okay, so here we have tyrosine, right? And when tyrosine reacts with this acyl chloride, we get two different products. Okay, we get two different products. Now, when the acyl chloride reacts with tyrosine, okay, it forms E, which has an ester linkage, and F, which does not. Okay, so now acyl chlorides can form esters with alcohols or phenols. Okay, carboxylic acid can only esterify with alcohols, but not with phenols. Phenol can form an ester with acyl chloride. So what we're going to get is an ester linkage over here, right? The oxygen from the phenol will bond to the C double bond O from the acyl chloride. So what we're going to get is, we're going to get this guy. So we get the C double bond O here, and then this carbon, the C double bond O, bonds to the oxygen from the phenol. It bonds to this oxygen, okay, and then we have the rest of the structure. Okay, we have the benzene ring, and then we have 1, 2, and we have an NH2, and then we have the C double bond O, OH. Yeah, and then compound F does not have an ester linkage, however, it does have an amine. So it will form an amide. It will form an amide with the acyl chloride. Okay, it will form an amide with the acyl chloride. That's also a condensation reaction similar to esterification. Now, when we get an amide, what happens is the nitrogen from the amine bonds to the C double bond O from the acyl chloride. The nitrogen from the amine bonds to the C double bond O from the acyl chloride. Again, the acyl chloride loses Cl and the amine loses its H. So what we have over here is, we have the C double bond O from the acyl chloride, and this guy will bond to the nitrogen, right? The nitrogen, which will now become an NH, okay? And then this NH is bonded to, this NH is bonded to a CO2H, right? It's bonded to a carbon that's bonded to a CO2H. It's bonded to a carbon that's bonded to a CO2H, okay? And that carbon over here is also bonded to this entire thing here. So that carbon is bonded to, that carbon is bonded to a CH2, which is then bonded to the benzene ring, right? That's the phenol over here. Complete table 9.1, drawing the structure of the organic product formed when tyrosine reacts with each named reagent. Ignore the directing effect of this substituent, okay, of this substituent. So here we have tyrosine again, okay, here we have tyrosine again, and we have to figure out the structure of each of these organic products, okay, when tyrosine reacts with each of these reagents. So let's say that first tyrosine is reacting with an excess of bromine aqueous. Okay, it's first reacting with an excess of bromine aqueous. So what do we get? So with aqueous bromine, right, the phenol reacts, and we have 2,4,6 substitution, but the 4 position is already occupied, right? There's already a group opposite the phenol. So there can't be any bromine here, but the bromine will go on the 2 and 6 positions, okay? So what we're going to have here is this. We have the OH group, and the bromine goes on the 2 position and the 6 position, okay, and then we have the rest of the structure. Okay, be careful not to miss anything when drawing the structure. When it reacts with an excess of sodium hydroxide aqueous, then what do we get? When tyrosine reacts with an excess of aqueous sodium hydroxide. So phenol and carboxylic acid are both acidic, so they'll both react with sodium hydroxide to form salt and water, right? They'll both be neutralized. So both of these OH groups will be deprotonated. Okay, both of these OH groups will be deprotonated. So we're going to get here is this. Okay, this guy will become a salt, O minus Na plus. You can just write O minus as well. You don't have to write Na plus. And then we have the OH group from the carboxylic acid will also get deprotonated. Okay, and then we also have to show the amine. That's the NH2. And then what if this guy reacted with an excess of nitric acid? What would happen then? So with nitric acid, we have a nitration reaction taking place, right? Electrophilic substitution of NO2, nitration of phenol. So the NO2 group, right? Again, the phenol is 2,4 directing, 2,4,6 directing. So the NO2 group will come at the 2 position. Again, the 4 position is already occupied. So what we get over here is this, right? We have a phenol, we have an OH over here, right? And we get an NO2 at position 2, Okay, and because nitric acid is an acid, right, the amine will actually gain a proton. Okay, the amine will gain a proton to become NH3 plus. Okay, NH3 plus. A mixture of tyrosine and lysine can be separated by thin layer chromatography. Under certain conditions, the RF value of lysine is 0.14 and the RF value of tyrosine is 0.45. Explain what is meant by RF value. Explain what is meant by RF value. The RF value is the ratio of the distance moved by the solute, okay, moved by the solute to the distance moved by the solvent, okay, or the solvent front. Suggest an explanation for the difference in RF values. So the question is saying, why does tyrosine have a larger RF value, or why does lysine have a lower RF value? We have to explain that. So what could be a reason as to why, let's say, lysine has a lower RF value? Why is it traveling a shorter distance? So in thin layer chromatography, right, the shorter the distance a solute moves, the more strongly it is attracted to the stationary phase. The stationary phase is the solid coating on the plate, right? That's the adsorbent, right? We have adsorption. So over here, since lysine is traveling a shorter distance, we can say that it's more strongly attracted to the stationary phase, to the solid surface of the plate. Okay, it's adsorbing more strongly. So we can say that lysine um, adsorbs, okay, adsorbs more strongly to the stationary phase. Okay, or we can say that the tyrosine adsorbs less strongly to the stationary phase. Similarly, the other factor that affects the distance is how soluble it is, or how strongly it's attracted to the solvent, right? Something that's more soluble in the solvent will travel a greater distance. So we can also say that tyrosine is more soluble in the mobile phase, right? That's your solvent. So you can say lysine adsorbs more strongly to the stationary phase, hence it's traveling a shorter distance. Or we can say tyrosine is more soluble in the solvent, that's the mobile phase, hence it's traveling a greater distance.